I'm John Preskill. I'm one of the organizers of the school. I just wanted to see my face. I'm happy to be here. I'll be all week and looking forward to getting acquainted with many of you. That's the reason I'm here. To complain about. And we're very privileged to have Barbara Terhal here. I know Barbara long. And, what percent on the topic?
Thank you. Okay. Is there actually a pointer or stick or just the laser pointer? Oh yeah. Yeah. Okay. Yeah. I upload, or the lecture notes were uploaded, I think this morning on the website. So if you want to follow along, you can have a look. And we'll add some corrections later. And maybe I've been a bit lazy. I mean, I was advised to use the board to give my lecture. And I think there is some advantage to doing that, to going a little slower. But then I also am kind of a messy person, so then I not always so successful in writing down things well. So I thought, well, I could also just use my lecture notes and then just talk about it, and then you can follow along, and then maybe sometimes I can sneak in a little bit more mathematical equations, although they may not enrich the discourse so much. I don't know. We'll see. Okay, so I'll give 3 lectures, and roughly here is the plan. So today I'll talk about some sort of a general questions, and I maybe stimulate some discussions about where we are with error correction and what are the most important things problems to look at. So theory versus experiment, some history. And then I want to discuss the quantum error correction conditions. So who knows here what the quantum error correction conditions are? Okay, so yeah, few, but not too many. So I think it's a good thing to know about if you're interested in error correction. And it's not, there's many more people who know these days about the Tor code or the surface code and the quantum error correction conditions. But also, given that there's been more interest recently in bosonic codes, I think it's good to study these and think about them a bit. And so I hope that in my lectures also I will spend some time talking about simple bosonic codes. So encoding a qubit in a bosonic mode in an oscillator. And the reason is that if you look at experiments, that actually they've done pretty well so far, particularly by the work in the Yale group. And I think we shouldn't sort of take for granted that we know everything about the best codes already. And so these new developments are quite interesting. And I've also, maybe in the 3rd lecture, I'll talk a little bit about a specific code called the GKT code, Gottesman-Preskill-Kitea, and some recent work we've done with this. Okay, so that's sort of here the bosonic code. And we'll go to the 3rd lecture. I want to introduce the stabilizer codes as a very general formalism that includes some bosonic codes. I also want to point out why stabilizer codes are so interesting. And then I'd like to talk about decoding also from a conceptual point of view. At least I hope to get the concept. Oh no, what's this? That's probably my power management thing. That's changed. Okay, we'll see how this goes. Otherwise, I have to change it. Okay, but you'll hear more on quantum error correction. So I'm not allowed to say much about fault tolerance. I'm not going to say much about logical gates. So if you have encoded your quantum information in from code, how you do logical gates. And I'm not going to say that much about fault tolerance either, because then Gottesman is talking later, and I'm sure he will cover those aspects. And Yang-Wan Ha is also going to talk about some error correction and self-correction, as I understand it. Okay, so that's the plan. And now Let's get started. So timeline. So 95, I would say that's sort of the first things also when I entered the field. We can place the origin of Shor's 9-qubit code, encoding 1 qubit into 9, and that code could correct one error. So if any one of those 9 qubits undergoes any error, it's either erased or its qubit is flipped, or there's another, phase flip error, you can correct it. And this was followed by the first scheme of how to do fault-tolerant quantum computing in 96, which was also a very important moment, showing that in principle, if we get error rates sufficiently low, we can do computation with, an overhead that doesn't kill any exponential speed ups that we may have with quantum computing. Okay, again, 96 was a great year, because also this was the time in which the quantum error correction conditions were developed. Maybe some of you know these conditions as the Knill-Laflamme conditions. So maybe I should have asked about who knows about Knill-Laflamme error correction conditions. And another more efficient code was discovered that year is the 5-qubit code. So similar as the 9-qubit code, it can correct one error, but it only uses 5 qubits. So you say, oh, great, we're doing better. But then if you look at issues of fault tolerance in logical gates, it's harder to, it shows that it's, obviously, that shows that it's not so easy to say, well, this does better than that. Okay, so then in 97, play the birth year of stabilizer codes, then Gottesman, as part of his PhD work, developed a very nice formalism stabilizer code. And also TTF's paper on the Tora code, which had earlier incarnations of gauge series and so on, but we can place its origin also 97. And then you could say the history covers lots of theory. And I would also mark this, 2001. It's a beautiful paper which has had a lot of impact in terms of kind of forming the blueprint of how we want to, make a quantum memory, namely using the Tora code, or actually a version of the Tora code with real boundaries, the surface code, for quantum computing. Okay, so lots of theory. So, and we started pretty early. So where are we now in terms of experiments? So this is a slide I prepared for some other talk. And this is just giving you a sense of, that we're sort of only really at the very, very beginning of doing something experimentally. So on this slide, I'm not listing any of the Bosonic code implementation, which I'll refer to later. So one thing to start with is to say, well, we're not encoding, quantum information. We just like to stabilize a bit using quantum bits. So we can use a 3-bit repetition code, replacing 0 by 3 zeros and 1 by 3 ones, able to correct one error, or maybe the 5-bit repetition code, to correct 2 errors. And so there's been sort of little experiments doing that. And one of the questions then, of course, in these experiments is like, what is your measure of success? When you publish your paper. And this is, of course, subject to subjective business. But you could say, well, if I can show that the encoded bit has a longer, lifetime, has a longer, the longer lifetime than one of the elementary constituent bits or qubits, then I can declare success. But clearly, this is not completely fair, because if you do computation on your encoded qubits and the encoded gate takes much, much longer than an unencoded version of that gate, then your lifetime also better be, much, much longer, right? So you really would like to look at the time it takes to do a certain gate versus your lifetime. Now, the Martinez group, and maybe he also mentioned this in giving his talk, they did, I think, quite a nice paper in which they looked at the 3-bit and the 5-bit repetition code, and they found evidence, say how convincing, that the 5-qubit code performed better than the 3-qubit code. And I remember asking him at the time, well, 7 qubits, so why don't we just first show we can store a bit convincingly, take the whole linear array of 30 qubits, I don't know what, and really show that the lifetime grows very rapidly with the amount of redundancy that you add, which would be evidence to show that really, evidence that really error correction helps, and the more redundancy you add, the more it helps. But I think they were more ambitious. Everybody wants to move to not just preserving a bit, but preserving a qubit. Which makes some sense, although I still like to see somebody preserve a bit with very long lifetime. Okay, but we want to move beyond storing bits. So what's the first code, which is a good code to do? And there's a little code with 4 qubits, and we denote it this way, but I'm not going to use this notation very much. It actually encodes 2 qubits into 4, so I get 2 logical qubits, but I can only detect a single error. Yeah? So that's the 4 qubit code. And Gottesman actually had an idea of, with current devices, how could you, maybe you can already test, how good this code does. And my student VO actually implemented some of that on the IBM Quantum Experience. And at the same time, IBM did an experiment also related to this code, and Maryland also did. And of course, the experimental papers declared that it was working, or that it was sufficient. And actually, my student VO, well, it was very hard because he wanted to see, he said, okay, I take my best qubits and I do an unencoded gate, and it has this post-selecting on seeing no error, because the error code can only detect an error. Post-selecting on seeing no error, what's my, how good is this gate versus the encoded version of a gate? And he had results all over the place. It was very hard to draw any conclusion. Right? And this is maybe what we could expect in the near term, that it is actually hard to draw, say, well, this really works. I mean, we believe it should work, but the error rates have to be sufficiently low. Okay, so then we could move up to the 5 qubit code, but the problem is that circuits for this one are larger, but there's new tricks to do this. So maybe this code will be done in the future. The next one is the 7 qubit code, but most of the effort goes to this 9 qubit surface code. But then you really need to have a larger system of 17 qubits. So, there are now chips of 17 qubits, but none of the people that are working on this have already, said, we have a chip that's really working. And there's a paper out that, shows the results. But that's definitely coming. Are there, please interrupt me if you have questions, of course. Any questions here? Yeah. Well, I mean, how do you say? Well, the point I wanted to make, I'm not being very precise what I call the lifetime, right, of my encoded qubit, because I have to characterize my encoded qubit with some error rate. Maybe it has an error rate for X errors, or for Z errors, or others, or maybe it has a different error model. And I can compare this. But okay, so sorry. I'm giving you the wrong answer. So okay, so lifetime is something that is in time, right? So the point is that error correction, it's the error correction routine itself takes time. A more neutral performance metric that we use as theorists is often saying, what is my logical error rate of my encoded qubit, right? And it doesn't matter how much time it takes to, for the error correction unit to run, but I just have some unit, and that unit has a certain error rate. And that unit, for example, maybe I did on the unencoded qubits, I did a Hadamard gate, and now I have a unit for the logical Hadamard gate that involves also some error correction, and I can just look at the error rate of that versus the error rate of my original Hadamard gate. Yeah, that's how we talk about it as theorists, but not everything we think about as theorists is taken over by the experimentalists, right? They have their own language. Yeah. Right. Yeah. Yeah. I have also, actually I didn't bring it, I have a very nice, there is actually surface codes that we call hyperbolic surface codes, that encode multiple qubits and I have a nice geometric picture of this, but I think for implementations, the connectivity between the qubits for those codes, it's a little bit harder to make it planar. And so the nice thing about the surface code is that if you see what measurements need to be done for error correction, it's planar. So that's why the surface code is favorite here. Other questions? Okay. Yeah, so what I want to do now is talk a little bit about error models, and in some sense this is a little pedantic, because it's kind of, okay, well, it's not so interesting. But I think the point I want to make here is about, if I think about, like, what should a PhD student working in error correction do next? Well, do some interesting theory is always good. But if you say, I want to help the experiments succeed, then you say, well, you'd like to be able to go beyond the error models that we have now, because they don't match really what we have in the lab. And then you're often into the realm of doing numerical, work, which you say, well, that's not really deeply interesting by itself. But I do think it's important. It's also important for decoding. And actually, it's a little bit of a pity because they're in quantum error correction theory. There has been now last year, people have developed neural network decoders, the machine learning decoding. And the idea behind those types of methods, so decoding is the process of inferring, what errors happened based on error information. Right? You're monitoring a system, and that's trying to, very broadly, that gives you information about what errors taken place. You have some assumption about your error model, and now you want to say, okay, based on the data I get, what corrections do I do? And so this type of task, you can say, well, can I use machine learning for this? And there is ongoing work, and I think quite interesting in trying to use this. And maybe this is also interesting if you were, can you, for example, learn, the noise model from the experimental data? So you don't have to have you don't use the toy model or something to model everything. So I think there's gains to be made there. But I'm not going to talk about this machine learning decoding, because I'm really not the expert in it, actually. Okay. So, but we've started using toy models because they're for ease of simulation, right? So the standard one is the polarizing noise model. Now you can relax this one. One is a model for a single qubit that undergoes, instead of the polarizing noise model, it undergoes some super operator, or some map S, which is trace preserving and completely positive. Yeah, so that's slightly more general. The reason I'm introducing this here is because these EIs, they will be very useful in talking about the quantum error correction conditions. You need to know what these EIs are. Okay, so now one thing about just a little math thing. So if you would have 20 qubits undergoing this more general noise model, I remember, there's also gates happening, but let's say every gate's perfect, and then I just insert some of the super operator here on these qubits. That gets very hard to simulate. So then, you can ask, can you kind of revert back to the easy model? And there's a nice way of doing this. It's called Pauli twirling. So if you have your density matrix rho, so you have this channel S, which is this more general noise model where with these operators EI, which are not necessarily Paulis, I first apply a random Pauli, I apply the map, and then I apply the random Pauli again. And that gives the twirled version of this channel S, or this map S. And that twirled version is always one of these depolarizing patterns. And the one exercise, because I have to give some exercises, is actually to prove this. It's not very hard. So what you do is you actually use, if you have a super operator S, which I had in the previous slide, there's a one-to-one map between this density matrix rho S and this super operator. If you apply this to a Bell state, it's Bell state. And then by looking at the other val states, you can see that the twirled version of this thing is actually, has the density matrix associated with the polarizing channel. And you can also extract the polarizing error rate based on the error rate S. Okay, now I want to make, so why am I introducing this? Well, one is because there's also a sort of continuous variable bosonic version of this that I'll mention later. And the other thing is that I just want to make a comment about error rates. So this slide has too many things, and this is maybe not deeply interesting, but it's something that comes up in practical questions about error correction as well. Like, well, how do I characterize my error strength? And how do I then characterize also that I've improved matters? And what's the measure of success? And so there's a variety of measures around, but I want to, so you could say, well, if I have some channel S, and I can look at, like, this channel is maybe supposed to be the identity, right, do nothing. And I can look at its action on half of maximum entangled state, and I look at its overlap, that's called the entanglement itself. Now, more general, people have also looked at diamond norms, which are, so you look at the channel, should be close to identity, and you look at sort of a norm, a distance between the identity, and the distance is defined at, apply it on sort of any state, but that state could be, more than that qubit that the channel acts on, and take then the trace distance between that. Okay, that's not, and I want to make a comment about this diamond norm because I actually like a slightly different way of defining a error rate, and the reason I like that is because it also allows you to define the Z error rate or the leakage error rate. Right? So there can be different sources of errors that you like to treat separately, because maybe your code is supposed to reduce, maybe there's more Z errors than X errors because there's more dephasing than, amplitude damping. And so you'd like to extract your dephasing error rate in some ways. And how can you do that? Now, one, I think, nice way of doing that is to look at this. So I can say, my S of rho is sum over E, sum over I, EI rho, EI dagger. But I can kind of purify this. I can say, well, this map always come about from some unitary of my system, which is where this density matrix low lives, and some environment, which is some state 0. Let's call it 0 E. And so there's some U that, applies this. Sum over I, EI, applied to the system, so EI acts on the system, and then the environment is in the state I. And then you clearly see that if you apply this unitary and you trace over I, you just get this action on the system. And then you can say, well, and then this is really the error. This is a coherent sum of errors that's really happening. And for every error, there's maybe the environment is in a certain state. So now I can group together certain types. Like, for example, I can say, well, EI is with some amplitude, it's doing nothing, right? It's putting no error. And with some other amplitude, it's doing this. And then if I say, well, okay, so I'd like to look at the total error amplitude. So how do I, so in general, what I would write, I have U on this psi 0 is with sum over alpha I, it's leaving the state alone. And then there's some error state. And so what I'd like to then, the total error amplitude is just the norm of the state, right? It's all the part of the wave function that has, it's bad. And in here I put bad and say, well, any error, X, Y, Z, leakage, whatever. Yeah. So I can take the maximum over all possible input states of the system, normalized, and that's the total error amplitude. Okay, so now let's look at, yeah. Total, why is it total error? What do you mean? Well, total, I mean, because I haven't split up, like, all this stuff is else, or, I haven't said, oh, this can be, you know, poly Z, poly X, poly Y. I haven't split up this thing. So I also call it error amplitude. But I want to, in the next slide, I want to split it up and say I only want to select, you know, having that the components in which I apply Z or Y to my qubit. And that's the error Z error amplitude. Right? And I could do similar thing that my EI operator is, you know, is a quantum jump operator to a level that I don't want, then it's a leakage error. Right? So so that's why I call it total here. Okay. This is not working. Why am I doing this? Okay. Okay, so like I already said, now again these slides are a little bit dense. It's the way to describe it this way. It's nice because you can extract some separate error rates. Yeah, so let's look at that. So okay, so what I would do for a single qubit, these EIs, I can always write them as linear combination of the poly, right? That's just the basis. And there are, you know, for a qubit channel, there are at most 4 of these I's. And so this is another little exercise. Why at most 4 cross operators, EI, exercise 2. I'll give answers to these exercises on Wednesday, so I'll upload the answer. And the exercises and the answers also just to, you know, just to add some random theory, or I mean, some random tools. Not random, but okay. So this alpha Aij is a 4x4 matrix because I have 4 polys, and you know, I goes from 0 to 3 also. So now, and I'm not sure this is so easy to follow right off the bat, but what I want to do is I want to say, well, all the terms that apply a Z or a Y, that the norm of that part, that's my Z error amplitude. Yeah. So that kind of looks like epsilon Z is the max overall input state, that's the psi S. And then it's Y applied to the state, right? The Y error is a Z and X error. Times some state for the environment. And this state I get from this expansion, you know, the expansion, there's another state in the environment. Now then I thought, well, what do you get? Actually, it's not so hard to show that the optimally have to do this max over the environment, and max over the state, and the state can be not just that one qubit that this channel acts on, but more qubits. And it's not so hard to show, well, that you actually, the optimal choice is that you would just take a maximum entangled state, because then the polys, you know, if you have you know, 0, 0 plus 1, 1, and if you look at what 2 polys do, they give you different orthogonal states. In general, for a single qubit, you don't have this. And because these are orthogonal states, there's this easy way this norm works out. Okay, so let me give you the upshot. So actually, epsilon Z is something that looks like the square root of something I call Py plus the square root of something called Pz. Okay, and why do I call this Pz, Py and Pz? And the reason is that I did now the analysis for some arbitrary superoperator S, but I could also look at the Z error rate if I twirl that channel, right? And I can look at how this compares. And this is the point that if I twirl the channel, so okay, so this is, maybe we don't need to go through the math here. If you want to ask me questions, you can do it later. But so the point is that if I take the twirled version of the channel, I get a depolarizing channel with error rate, and I would say, well, the total Z error rate is Py plus Pz, right? And what I calculated was epsilon Z was an amplitude. So to get back to error rate, I need to square it. But I showed that the epsilon Z was the square root of Py plus the square root of Pz. So if I square that, I get Py plus Pz plus this stuff. Okay, so what this is, what the goal of this exercise is to show that if you twirl the channel, and you look at what effective probabilities of errors you have, you're not necessarily capturing the error strength, right? Because you have The twirling is so the effect of the twirling is first random poly, then the channel, then the same random poly. And what the effect is that if you write this channel as something like this, I can expand I in terms of polys, and then I get cross terms, pj, rho, pk. If I twirl it, these off-diagonal terms drop out. So the only terms that remain are when j is equal to k. So I kind of take it's also a way of saying this is, sometimes people call this a chi matrix. This is what they measure in experiments with tomography. And if the twirl channel has the chi matrix, which is diagonal. What do you mean? You pick a random, if you just, flip a coin and you pick one of them. And it's the average, right? It's just a stochastic thing. So you write on average what it is. Yeah? Yes. Yeah. Yeah. So the twirl, when you twirl a single cubic channel, you get a polarization channel. Because you get just it becomes diagonal. You become, with some probability you do identity, with some probability you do an x, with some probability you do a y, some probability you do z. Then, if you look at the twirl channel, then the error rate of I have to put some water. Sorry. Then the error rate of a z error would be py plus pz, right? But my point here is to say, if I were to not twirl it, first of all, I have to talk about error amplitude in this analysis. And I can interpret it as an error rate by squaring it. But then that number would be equal to something that's more than py plus pz. So some people worry, there's been work on saying, well, how do coherent errors fare, do they fare differently under quantum error correction? The problem is you can't simulate coherent errors so well. After I do quantum error correction, is the effective error model, does it more look like the polarizing channel? If it turns out to be true, then it has fewer coherent errors. So there's research in studying whether using the polarizing knowledge model captures the right effect of quantum error correction. Sorry, my throat is a little bit acting up. Yes. I don't know, because I haven't worked on entanglement breaking channels recently. Here. You can make, yeah, right. But I don't think there's been, yeah, I don't know about research in this direction so much. I mean, yes, yeah. Yeah. Well, the point is to say, let's say I know my error model is, my errors is some super operator S. But I can't do the simulation, numerical simulation using S. So instead I use the twirled version. And I get some data saying, well, if these error rates, the Z error rate is below something, this code will help. And now the question is, are these results are actually reliable? Because in reality, my channel was the non-twirled version. And in some sense, it has a higher error rate than this one. Right? And this is only just giving you a hint. And actually, there are papers that say the results are all over the place. It's not there's not a very clear measure to say, well, this is the character of the, how do you say? There's work by David Poulin on this, which shows that using different measures of errors shows you can show different behavior. So, but this is just to say word of caution by using a twirl channel as a stand-in for the real channel. I mean, it's also saying, well, we should really try to do more stimulation. I mean, there's many more things that one can say about it. Of course, you can say, well, maybe in the lab, I could also just twirl the channel, right? After every gate I just do a random Pauli. And then, or before the gate I do random Pauli, after the gate I do random Pauli. And now if these Paulis are actually very high fidelity, I don't make my life much worse, but I make the error model very nice. So I'm not sure, maybe there was some paper that I don't know whether this has been done. I vaguely recall something, but I'm not sure. But I can imagine this could be an option. Other questions? Okay. The question is like, what error model you should use, and how should you measure the error rate, right? What quantity should you use? And I think my answer tonight is there's not. I like to use this in some sense, but there's not a very so it's not a good. Well, it's not a very simple answer. I mean, the point is that if you look at the Torah code, there's a threshold error rate, 1%. But now I put on coherent errors. Now, where is that 1%? What does it relate to? Right? So should I equate it with this quantity or something else? Right? So that's still the question. Okay. So now another caveat. So I said there are toy models for errors. So another caveat for errors is the correlations that error have in space and time. And I think both pose some problems also for simulations necessarily. So let's talk a little bit about space. Now, one typical situation is that, time. Typical situation is I have a qubit, which is some 0, 1 energy level splitting, and that difference is fluctuating in time, but it's fluctuating very slowly. People call this 1 over F noise. And so you have some delta, which is, how it changes, some random variable, it changes in time, and on average is 0, so the qubit has frequency omega 0, but it's correlated in time. So this is the expectation value of this random variable, and maybe it's time translation invariant, meaning that this is only a function of t minus t prime. And then the something called the noise spectral density is defined as the Fourier transform of this. I'm not doing this very precisely, but it's only roughly. And so for 1 over F noise, the scale is 1 over omega. So for very small omega, this is very large. So there's a large Fourier component. So meaning that that's a dominant sort of, dominant part of this correlation in time. And now, and if these drifts are slower than like the duration of your several quantum error correction cycles, it's also a little bit awkward how to deal with it numerically. How do you simulate this noise model and so on? Okay, but these are just comments. I don't really have a good answer. I have a PhD student who's looking into incorporating this into his analysis. I don't have, this is not part of the sort of answer set up. And it's also known that if you have such slowly correlated noise, then called dynamical decoupling techniques, they're often more useful than quantum error correction. That's for the idea of dynamical decoupling. The simplest version is just spin echo. Let's say I do some rotation for a single qubit around the z-axis by some small angle, and that's an unwanted rotation because it comes from this delta, being non-zero. Now, if I do a very fast pulse, which is just doing an X, Pauli X bit flip, followed again by, more rotation, and again, a Pauli X, then if you look at what this does, if you write this as a matrix with easily IZ and so on, X just anti-commutes, so there's a sign, so this becomes RZ minus this angle. And, this combination with that is the identity. That's the spin echo idea in a nutshell, and they're more clever techniques. So the nice thing about dynamical decoupling techniques is, of course, they don't take more qubits, they just take more pulses. But, sometimes you cannot get rid of every slowly varying noise source by doing that, so you still have to examine how this affects some, your error correction. Okay, but I haven't seen many papers, or actually not many papers focused on experimental things on this. Yes? It's errors over time, errors over state. It's the Hamiltonian has parameters which are correlated in time, meaning that if the frequency is higher now, it's also likely to be higher later, right? And that's captured by this this correlation function. No, delta is a parameter here. Sorry. This is just a classical parameter, so this is sorry? How do you define the expectation value? Well, this is defined in a very sloppy way, right? Because I have to look at the, so I could define something like a Markov process by which there's some probability that at some time this has some value, and then there's a chain that says if this has a value at time t, then the probability that the next value is, so let's see. So, P, geez, where's the chalk? Oh, there. Let's see, delta, whatever, t prime or t plus 1 is, so there could be some but the point is that there is not even, I just had a discussion recently with somebody who says there's not really good models to simulate 1 over F noise. Sometimes it's done with what's called random telegraph noise, and you have a lot of these. And so, but this is something that you can have a set of a Markov chain, and you have, say, maybe from time t to t prime, there are many of these steps. And so that induces correlations between what you have here and what you have later. But then the question is, can you model, because of course this function is not completely well defined, right? It blows up at omega, so you have to, regulate that in some ways. And so you have to have a transition matrix that gives you actually that behavior, which is not trivial. And I'm completely not, I'm not giving you any solution to this. Okay. Okay. Now the correlations in space, I think they're even more potentially dangerous in some sense. So usually you say you have a 2-qubit gate, and in your usual error models, and also the theory of fault tolerance is built on this, where you say, well, if this gate can fail, so maybe there's some errors on these 2 qubits, and maybe, these errors are correlated, right? It's not like this qubit undergoes some channel and that qubit undergoes some separate channel. No, they can be correlated. That's fine. But, there are other qubits in the game too. So maybe if I do, the pulses or whatever to do this gate, there's another qubit that's sitting there that's also affected. And this is actually very common because, well, if you look at any device, you have interactions that are just, solid state, like superconducting qubits, they're just there, right? The hardware is just given. So there's coupling between qubits in real space, meaning on a chip, depending on what physical material you have there. I'll show a picture. And one very important thing is that so I've been interested in superconducting qubits, so if you read, how you do gates and so on, it's all about resonances and frequencies. This, first you have to have a coupling between two qubits. And then, if this qubit can lose its energy, this qubit can lose energy, and that packet of energy can be absorbed by the other qubit because it's the same amount, then, that interaction is strong. And if it's off resonance, it's not strong. So you have crosstalk all over the place. And the only reason, so why is it? It's kind of neglected, but it's not. The point is it's neglected in our models for fault tolerance because we don't know what it is. So very roughly, if you talk about superconducting qubits, at some level what we have is an anharmonic oscillator. So this qubit has 0, 1, and then a bunch of higher levels, which we hope we don't get, we don't get excited, and they're, it's anharmonic, so this level, the energy splitting here is sufficiently different from the energy splitting there. And then there are also some harmonic oscillators. These are typically resonators. And so they are microwave, in this superconducting systems, they are microwave resonators with a bunch of resonance modes, with integer, with frequencies, and then you select one of them that you're going to use maybe to have qubits interact via, or you populate with photons. And so there's a bunch of qubits, bunch of oscillators, and then there is a way in which things are coupled. So here, for example, this is a very dense thing, but this comes out of a paper of the Delft group, of a layout of their plans for surface 17. And these colored dots are the qubits, and each qubit is planned to be a structure like this. So this is a piece of superconductor. This is a piece of superconductor. Here, this is two Josephson junctions, two Donald junctions, like what David mentioned. There's a little hole here, which means that if you add magnetic flux through this here, it changes the frequency of this qubit that is realized in this. And then there are arms here, which denote where it's coupled to. So this is a capacitive coupling. You just have two pieces of metal, right? So there's a capacitive coupling here, but in this case it's superconducting. And this piece of hardware then is a coupling bus. So we treat that as a harmonic system. So this guy has 4 of these couplers through which this qubit, there are 4 buses denoted by these wiggly lines, these resonators, by which it can couple to other qubits, because we need that type of connectivity for a surface code. And the colors here denote these qubits have different frequencies. And so we would like to have, we like qubits to say, these 2 qubits, we don't want them to exchange energy or couple if we're not doing a 2-qubit gate. So you actually in these schemes, you tune the frequencies of these qubits to do a gate, right? But the coupling is always there. It just, it's just effectively weak. But the problem is a little bit like if you have many couplings that are weak, they add up, right? And it's quite hard to classify to how much they add up. Do they make the difference between sort of a quantum error correction scheme working to not working? And I think in that type of setup, only in numerical simulations, but they get kind of large for 17 qubits, can tell us a little bit, give us some information about how bad it is. Okay, I don't want to say only. I think more theory can be done too. Okay, so yeah, so that's a little bit about crosstalk. And then maybe I have another comment about this. So that is the question: how well do concept of fault tolerance work in practice for small code if you have crosstalk? And here it is a very small example of this, where you say, well, let's say I want to swap qubit 1 and 2. Of course, if I apply this swap, I can do it via 3C NOT gates. I could have, the problem is that if one of these gates fails, I'll have some error on both qubits. And I can do something more clever, in principle, by saying, well, I have a dummy qubit that I don't care about its state is. And so I first swap this one with that one, and then I swap this qubit with that qubit, and effectively, I can swap qubit 1 and 2. And then the thing is that if this gate fails, Well, there'd be an error maybe on the dummy qubit and here, but I don't care about the error on the dummy qubit. And similarly, if this case fails, I'll have an error on the also only on this qubit. Yes, but the problem is that this assumes that if I do this swap gate here, that there's no, like, doing that swap gate should not sort of induce extra errors on qubit 2. Or at least this is the assumption, but let's say this happens. So if you, then the advantage of such a scheme quickly sort of goes down the drain if doing, swaps between these neighboring qubits induces a higher error rate on sort of spectator qubits that are not involved in the gate. Right? Okay, again, this is kind of sketchy and not showing any resolution. It's just a question of how can we address how well fault tolerance work in practice. Okay. Oh, wait a moment. This is actually in that. Yes. So now, how am I doing with time? Yeah. Okay, let me just see. Oh, 35 minutes. Okay. Okay, now I just brought up the other thing. Okay, let me just say the point I want to make with that slide. Yes. With the swaps? Okay. Yeah, actually, this is maybe not the full swap, right? Because I think this qubit gets over here, and then it gets over there, but this qubit is only swap, but this is not even the full swap. Right? Is that what you're on? Is it? Well, okay. The point is that you can, if you say, I have a 2-qubit gate. If I do a 2-qubit gate, I have some error rate in which the gate fails. Let's call that P. And if the gate fails, I expect that there can be errors on both qubits. This is the danger of doing 2-qubit gates. And so in order to, so that's why if I want to do a swap between qubits 1 and 2, I may not want to do that swap directly. I may want to do it in a sort of fault-tolerant manner in which I involve another qubit, so that if this 2-qubit gate fails, it just puts an error on this dummy qubit, and I don't care about that. Right? That's the idea. But this is actually, I've been sloppy about this. I should correct this. Yes? Yeah. No, you swap. No, the thing is, okay, so the dummy qubit just okay, so yeah, I mean, this circuit is misleading. I swap the content of the register, right? So the dummy qubit, if I swap, let's say, well, okay, so depending on, okay, you have to be careful what it says when there's an error here, right? Let's say there is this dummy qubit gets an error here and it's swapped, so then the error is there, right? And the good qubit may also have gotten an error and it's here now. And then it gets swapped with this one, and then that good qubit, well, that qubit just has a single, the point is that there's a single qubit. It's not that there's no error, it's just a single qubit error. Okay, I think there's I'll improve this slide maybe. Is there a question in the back? I can't hear you so well, sorry. Well, I'm saying, like, this type of circuit would work if there's no crosstalk. The benefit of using a circuit by which you swap via dummy qubit so you don't have 2-qubit errors may be non-existent if we have too much crosstalk. And this depends on the error rate for crosstalk. Let's say if I do, if I have qubit 1 interact with qubit 2, and there's a spectator qubit 3, that then, undergoes maybe half the error rate of the ones that 1 and 2, then, what can I tolerate? Or it may be a tenth, or it depends on the numbers, right? How bad it is. Yeah. Yeah. So this is, this also feeds into the, there are two things. This is partially covered a little bit by this 1/f noise, in the sense that some classical parameters in your gate can be non-Markovian, can have time dependence. And I actually know this, there's an experimentalist in TU Delft who's tuning up his control Z gates for superconducting qubits, and he finds when he does one control Z gate, the next guy is actually different because he just did it, because he does a control Z gate by adding flux, so producing a local magnetic field, but there's some kind of hysteresis. There's still, the parameters are changed, and that affects, and he has to try to calibrate this out, and this is problematic. So that's a classical, well, it's part of the classical description. There's also things about, sort of quantum degrees in the environment that have correlation, right? That you need to be more of a quantum description. But, we also have, just the last comment, we have, John Preska worked on this and I worked on this too. It's not true that fault tolerance doesn't work if you have non-Markovian error. We can treat error, we can, the reason that error correction of fault tolerance works, but I was not supposed to talk about fault tolerance, so, is because of the locality of errors, and that the error rate is sufficiently low. And I think the locality of error says, like, if I have k errors, the error rate scales like some epsilon to the k. And k errors on, k different qubits. And there's not a Hamiltonian nature that couples k different qubits as one term in the Hamiltonian. Physics is sort of made from interactions between very few degrees of freedom. Why is that? Because they're local degrees of freedom. But yeah, that's sort of a rough answer. There's also, John Preska has also written a paper about dealing with non-Markovian noise in full tolerance setting in a general way. Any questions? Yeah. Well, diamond norm. Okay, so there's two things about the diamond norm, and one thing I actually didn't mention so well. One thing is, one thing is that you see here that actually you compare S with identity channel, and it's not like in identity channel times something. And actually, if I do this, see, the thing is, this analysis actually relates to the diamond norm indirectly. But here, there's a chance that I say, well, I can compare S with any channel, there's some beta times identity, right? And I just optimize for beta. I just want it to be, that should be allowed. That's one thing that I think usually in this analysis, if you compare S with the identity channel, that's not entirely optimal. And that's captured in this formalism. And the other thing is that if you say, well, okay, so how do I, okay, you can, using the diamond norm, you can also define a Z error rate and so on. But I chose to present it this way because I find it more intuitive. But we've written a paper with DiVincenzo, Stefan, me on bias noise qubit, and we use actually the diamond norm to calculate sort of Z error rate and leakage error rates and so on. But we do it with this, yeah, sorry. Yeah. How do we find what? How do you measure the error? Okay, so of course this is a different thing. Let's say I could do, tomography, process tomography on a, single qubit gate, which is sitting there. That would give me, in principle, the error channel, these EIs, right? But the problem is, of course, that this also doesn't scale process tomography can't do it for many qubits, so that's a different question. Yeah, so there's a, yeah. Okay. Yeah, but you don't need to, you just, well, this is why this analysis is, I think makes this more clear, that the, let's say S, alpha identity minus S is smaller than identity minus S. Then I would say the error rate is the smaller of the two. Is the smaller one. Because I don't care that it's the, what, sorry? Well, okay, that alpha is not, that's not really fair. Okay, yeah. Yeah, that's not very, that's not the, that actually gives you the, that gives you 1, so that's not a very, so okay, you can do that, but if alpha is 0, then it's the diamond norm of a super trace preserving map, which is just the trace of the density matrix is 1, so it gives a very bad error rate. But if there is a lower error rate you can get by choosing a non-zero alpha, I think that's okay. Because of this type of analysis. Because we just care, like if because if you do the unitary expansion, you just care, there's some amplitude for doing the identity. I don't care that it's like, it's not 1. That total amplitude is not 1, right? I mean, I think you can convert back this analysis to this diamond norm stuff, and you'll see that it relates to allowing, saying I subtract, alpha identity minus S, where alpha can be anything. Okay. Other question? Or should I switch? So, okay, so I can start with the second part. Okay, so I talked a little bit about quantum error models, and I'd like to continue with that a bit. Because, where did they come from? I talked about some toy models, some general trace preserving superoperators, but then what we usually have for the simplest models is we have things like this. If you say I have a qubit, 0 has different energy from 1, it's in contact with the thermal environment, 0 temperature, then with some probability 1 will drop down to 0, where 0 is, will stay 0, right, just from energy. And that's modeled as an amplitude damping channel, where E1 is this sigma minus, going from 1 to 0 channel with some parameters. And there's also, there's phase damping in the simpler model, but it's actually equivalent to a phase flip channel. So with some probability, nothing happens to my qubit, with some probability, a Z error happens. And then if you combine these two, I see these are just sort of examples of these EIs. If you combine these two, you get something, a typical single qubit error model, where your density matrix rho is mapped onto this density matrix. And these are the matrix elements. And so what happens is that the amplitude for 1, the probability for 1 goes to 0. All amplitude eventually at a long time gets to collect to 0. Yeah, and so the reason to stress these EIs, as I said, is that they relate to the quantum error correction conditions. But now I'd like to look at some bosonic error models. Okay. So to motivate some codes that use bosonic error correction, because I think one of the nice things about bosonic codes is that they've come about from people who are, think what is my experimental setup, and that's one. Then what code do I want to make for that? And that is a good strategy, but at least some of it, I think, the short term is an interesting strategy. Okay, so if I talk about bosons, what I just mean, I just have a single harmonic oscillator, some annihilation and creation operators obeying commutation relations, And I'll be using these operators, sometimes called quadrature operators. They're two Hermitian operators, satisfying this commutation. Sometimes they're defined with 1 over half instead of 1 over the square root of a half, which always causes a lot of sort of paper writing agony, whether you keep track of your square root of a half and so on. Okay, so the Bosonic codes that have been, researched in the group by Yale focus on photon loss, because if you if you have a microwave cavity, and they have very long lifetimes, milliseconds even, but the predominant source of errors is just photon loss. And so that photon loss is this very simple model you can model by some Lindblad equation, your density matrix rho representing your bosonic mode, and some Hamiltonian H, which is just the Hamiltonian of a harmonic oscillator, and then these quantum jump operators of a photon loss channel, or this Lindblad operator looks like this. I don't know, are people familiar here with Lindblad equations? I think that's mostly, yeah. Okay, so the one thing is, I don't know if people want to do a hard exercise, is to say, okay, that's my Lindblad equation, that's time dynamics. Now from that model, I want to get a superoperator representation. Now that's not very hard to do when you just look at very, very short time. And then of course you say, well, then, I just apply the short time evolution repeatedly, and then I get the long time superoperator. Right? But then I may not get a very neat mathematical expression for this. Because the short time evolution maybe has two Krauss operators, these EIs is two Krauss operators, say. And then, if I repeat it, then I get, many, many Krauss operators. So what is nice about this channel is there actually is a way of exactly writing the Krauss operator representation at any time t. With this H, you can always go to the rotating frame where it's gone, and it doesn't change this operator. But these ELs turn out to look like this. And it's actually not so easy to derive this. And so if anybody wants to, try a hard exercise, you can do something similar, but I have not, maybe you know this. For the case where you don't have photon loss, but also photon gain in a thermal environment, there's also an expression like this, right? But which paper is that? Do you know which paper that is in? The A dagger, right? You have some A dagger to the P, A to the Q. Yeah. But I was wondering where it was derived, because I don't know where this is. Okay. Anyhow, so okay, but this looks complicated. But what you see is that there is Krauss operators going from 0 to infinity, and they have some, every one of them has some 1 minus gamma to the n over 2 times A to the L. But this expression is not so intuitive, and so anytime I can write this expression. So okay, so there's time here. So where goes my time? So I have the definition gamma, and gamma is 1 minus e to the minus kappa t. So this rate, the loss rate, which is a function of t, can be put in here. And so this loss rate, of course, goes up. Right, it becomes, for a very long time, it becomes 1. And of course, then this blows up. So this is a bit of an awkward expression, because you can't, deal with these limits, because there's just, infinite number of these and so on. But the intuition is that for a very short time, it's dominated by, having a single loss. That's one of the operators, and the other operator is no loss. But then they have to form a super operator like this. And then if you go to longer time, there will be multiple losses. So there's some. So the point is that for a very short time, only L is 0, which is no loss, and L is 1 kind of contributes. And for longer time, there's more. Yes. This if you're just a beam splitter, so you have another mode, and you have a beam splitter interaction, which is beam splitter, not very weak interaction with this mode, and the other mode is in a vacuum. So you just as part of your thing splits off, so you lose some photons because they go to the other mode. Yeah, just quadratic. Yeah, and you can actually derive, one way of deriving this is going to that interaction. And if you in the thing where you have the other mode in a thermal state, you get both photon gain and loss at a rate that's determined by the temperature of this environment. Okay. Yeah. So for small kappa t, it's kind of more intuitive, where you if you have to integrate the Lindblad equation, it looks like something like rho of t is either the L here L is the total evolution on rho of 0, and for small time I can just expand it 1 plus L of t, and I can extract my super operator from this description. And that's how I can get the super operator. And if you do that, you get these two guys. I used to get the E1 is photon loss with some amplitude or square root of kappa t, and E0 is no loss, but it's not just the identity, it's this guy. And the reason is that E0, we have to have this condition this is the identity, and in this description, this is the identity, not exactly up to some corrections in kappa t. Okay, so this is an approximate short time description. So it depends. If it depends on what state it is, right? So if I have if I have a coherent state, sorry, the it usually it just leads to going to the vacuum. This channel just maps every state onto the vacuum after a sufficiently long amount of time. It preserves the trace of the. It preserves the trace. Yeah. But no. Yeah. Okay. So the point is, the quantum error correction condition that we'll talk about will be focused on what's here, right? So if I have this channel, let's say, well, I'd like to have a channel that corrects, deals with photon loss as an error instead of a polyflip. I have this operator A, and also perhaps this operator N, or this particular combination as an error, right? Now, one thing before we go talk about this more, there is you have to. Okay, so another type of error, which is the following. Let's now say we have my Hamiltonian is this harmonic, but there's also an anharmonicity, some current nonlinearity, and let's say if there's no photon loss, well, this is just then a systematic error, right? It's just an extra rotation, and if I know what it is, I know what k is. This is not k, but kappa. This is k, not kappa. It's a systematic error. I can compensate for it. I can go to a rotating frame in which I just co-rotate, and fine. But the problem is if you combine it with photon loss, and the problem is that the math here, I just want to give you the idea, then it leads to additional dephasing. And one way you can roughly see this as follows is that if you'd have a photon loss error, let's say you go to a frame in which you you rotate with this Hamiltonian. So now you have to look at operators in that frame. So you have to look at the photon loss in that frame. So you look at this type of quantity, and this conjugation of the Kerr effect with the Kerr Hamiltonian with this gives you something like this, where it's again A. There's some phase. That's okay, but it's an additional rotation. So if I know when the photon loss happens, I just say, okay, there's an additional rotation done, fine. But of course, I don't know necessarily when the photon loss happens. I'm just monitoring, and my oscillator is sitting there, and I'm waiting. I'm not monitoring anything. And, in that time interval, the photon loss could have happened right off the bat or a little later. And depending on these two cases, I had an additional rotation, an additional evolution like this happen or not. But I don't know which one it is. So that we call dephasing, right? Because this, if I were to use the Fock states as level 0 and 1 and etc., they will pick up, 0 will pick up a different no rotation, and 1 will pick up an additional phase factor, right? So different Fock states pick up different phase factors, and I don't know what the phase factors is, so this is called dephasing. Yeah, so again, if you just look at what this noise model with this current nonlinearity looks like at lowest order in kappa t and kt, you have two. It's sort of similar to my previous slide. You have two cross operators. One is this one, again, photon loss, and the other one is responding, evolve and lose no photon. This is sort of what this means. So this is the time evolution part, and this is the no photon part. And this is again approximate. These are not exact. So again, what the reason to put this slide up is say, okay, if I know that, then I maybe want to design a code that can correct this error, and maybe this one and HK is A dagger A squared. So also maybe A dagger A squared. Right. So that's these types of models provide motivation. Okay. So how am I doing on time? I don't have a watch. Is it 10 minutes? Okay. Okay, so now I move now to another way of describing errors on a bosonic mode. And there is an advantage for doing this, and there's a disadvantage for doing this. And so we know for qubits, we just take their Pauli errors, and I've already said they're not necessarily, they're toy models, and so they have some nice advantages, but they, coherent errors maybe behave slightly different. And so we have our Pauli error model for bosonic mode, our displacement. And so what you'd like to have an error basis. What is an error basis? It's a bunch of operators such that any operator can be written as some linear combination of those operators. Now, because this is a bosonic mode is an infinite dimensional Hilbert space in principle. It's not just a linear combination. I have an infinite number of these. The basis is infinite dimensional, right? And I have to have an integral here. So the basis. So if you're familiar with displacements, so I introduced these p's in the q, and I can. This is sort of phase space. I can look at states if they're with their expectation value with respect to p and q. Then a displacement like this, for alpha being a complex, if I apply that to the vacuum, I get a coherent state alpha, which I can write in a Fock base like this. So I don't know, I think that's probably something that most people are familiar with. And if this is some other state beta, another coherent state beta, then if I apply alpha to it, it becomes alpha plus beta plus a phase factor that I've not written on the slide. But it's essentially, if I look at the state alpha as, it has a real and an imaginary part, which are the two coordinates here, then the alpha is a translation in phase space. Okay, and so now there is a is a result that was, I think, originally from in this paper, proved in this paper. And you have to be a bit careful with these results because it's always infinite dimensional Hilbert spaces. So in principle, things are not really well defined. But of course, we're always, in practice, we always look at a finite part of this space with a finite number of photons. So we always put on regulators and, you know, but so, you know, we know what we're talking about, but yeah, anyhow, we're physicists. So, okay, so any error can be written as a, as an integral over displacement times a prefactor. And this prefactor could in principle be obtained by doing this. And this is, of course, very similar as writing any, you know, any 2x2 matrix can be written as a linear combination of Pauli's with some coefficients. Okay, but these, of course, this displacement error model. Okay, so and then you can. Okay, so this split. Okay, sorry, didn't go ahead. So then I can define a kind of bosonic equivalent of a depolarizing point model, where I took my Pauli errors and just say, okay, well, they happen with some probability, and now I just say my displacements happen with some probability. And so that's the Gaussian shift or displacement error model. And now I've unfortunately switched notation a little bit in the sense that I've not expressed it in terms of displacement, because I could go back. So there's a density matrix rho, and then the displacements happened on it, you know, and u and v are related to the imaginary and the real part of alpha. And u and v are two parameters taken from some Gaussian distribution with some variance sigma p, maybe for sigma p squared for u and sigma q squared for v. Yeah, so and at that level, this is just a toy model, but it's a very convenient toy model to do analysis. So we just finished the whole paper using this toy model. But then one has to motivate this a bit, and this is a paper that Kuhn also worked on, and Young, and it's actually not so simple. So let me just place a few comments. First of all, is I can do something like the twirling, the polytwirling, right? What was polytwirling? It was converting any channel on a qubit to a depolarizing channel. Yeah? So now I have a single bosonic mode, so I can say, can I convert any channel on a single bosonic mode to a displacement channel? Now, maybe that displacement channel does not have Gaussian weights, right? So in this case, I chose the probability for displacement to be a certain way. They were independent for the real and imaginary part of alpha, and they're Gaussian, right? But I can also ask, you know, can I just at least make it that this is a probability over u and v, right? That would be a sort of a general mixture of displacement channel. So you can define some twirling where you say, okay, have the density matrix, apply a random displacement, apply channel, apply a random displacement again, or the dagger in this case. But that's a little bit unphysical because, of course, a random displacement is a random translation over an arbitrary distance. So you have to kind of regulate this with a with some Gaussian. So in principle, this is possible, but it's I don't know if it's not. Yeah, okay. In principle, it's possible. The other thing is that how does it relate to, in terms of rate, to interesting channels like photon loss is physical, or maybe something there you have a small rotations like we also saw that led to dephasing, like it's small unknown rotations. And let's say this theta is a small parameter. Then you can ask, and we actually wondered about this when we were preparing this paper, can you write, like I said, that any error can be written as a integral over displacements with some weight in front of it. So if the rotation is small, can I then do an expansion in terms of small displacement? So the alphas, you know, the real and imaginary part of alpha is small. And this is not necessarily the case. So this is a subtle point. And for example, the only thing I want to illustrate this. Think about it as with this rotation. Let's say I have a state which has really a huge number of photons, so it's very far out of phase space. And this e to the I theta a dagger a is a tiny rotation. Then, of course, because it's a rotation, because the state is so far out, it's still a big move in phase space. So that tiny rotation, I definitely cannot write as a linear combination of small displacements, because they will only move the space in a small region of phase space. Whereas because the state had so many photons, was so far out, it has been moved a lot. So that's a kind of caution that this type of transformation is non-trivial, and it may depend on saying I only consider states with upper bound on the number of photons, and in that part of space I'd like to express, other noise with small error rates in terms of small displacement. And you can do that in principle. Now there's another nice result, and I think this has also been derived in various places, but it's also shown explicitly in this paper, that if you follow a photon loss a channel, like the one we discussed before, by an amplification step, meaning that you now let the mode A interact with another mode B, and the transformation induced is something like this, where G is some number larger than 1. So it is an amplification, right? If I look at the A dagger A, it gets a factor of G in front, and some other small effect due to this. But it amplifies the intensity, or the number of, increases number of photons. Then you can actually analytically see that this induces a Gaussian displacement channel. So I think this is a very nice result. At least to me, it was surprising that this was the case. Okay, so are there questions? Yeah. So now I'm starting. Are there questions on this? Because now I'm starting with the quantum error correction conditions, but I think we should start with that in the next lecture. So, yes. Yes, I think that's not the case for the photon loss necessarily, but I'm not actually sure. We don't have. I'm not sure we actually proved this in the paper. Yeah, but that's with the amplification. But if you just take the photon loss itself, the argument, I don't know, the argument I gave for the rotation, that is sort of, you can't write it as small displacement, doesn't work there. But I don't think we have another argument. I have an argument in another paper which shows where you have an upper bound and a number of photons, how you can write it as in terms of displacement. But other than that, I think there's not. I mean, I'm looking also at Jung. I think there's no. Well, it's true. Yeah. Okay. You're yes. Yeah. I guess you're right, because you can. It is also a big move. If you say I have a large, like I have some minus kappa, A dagger A, and kappa is really, really small, this can still be a big move in phase space. Yeah, I think you're right. Yeah. So that's another. Yeah, sorry. Yeah, but I did have the thing that it was slightly different than this. But sorry. Okay. Other questions?